Hello, everyone. Welcome back. Today, we're going to take a look at chemical reactions and continue our discussion on the chemical basis of life. Last class, we left off talking about chemical bonds. We talked about how chemical bonds are used to form compounds. All right. So chemical reactions make and break chemical bonds. So we looked at the water molecule. The formation of water from hydrogen and oxygen is an example of a chemical reaction. The composition of matter is changed as bonds are broken and formed to convert reactants into products. So when we look at life and the fact that we are a big bundle of chemical reactions, there's tons of metabolic activity going on, catabolic and anabolic reactions going on. These chemical reactions are due to the presence of these chemical bonds. And so we represent what's happening in a chemical reaction using chemical equations. And so the way that these reactions are set up is that on one side of our equations, we have reactants, which are the substances that are involved in this reaction. And then we have our products, which are the newly formed substances. Okay. Chemical reactions do not create or destroy matter. They only rearrange it in various ways. So it is important for you to understand this concept of chemical reactions as we further explore how atoms and elements and compounds are formed. The water molecule is an example. All right, so we've got hydrogen atoms and we've got oxygen atoms. The reaction leads to the production of this water molecule. Okay. Let's talk about water in a little bit more details. We mentioned before that water is a very essential element for sustaining life. There are various properties of water that we want to be familiar with, okay? Hydrogen bonds make liquid water cohesive, right? We identified hydrogen bonds as a type of weak bond that is very important to sustaining life. So what is cohesion? The tendency of molecules to stick to the same kind of molecule. We see that in water, this property known as cohesion. We're going to identify some properties of water that you should be familiar with. Cohesion, the tendency of molecules of the same kind to stick together. Okay. Another property is adhesion. This is the tendency of two kinds of molecules to stick together. We see adhesion. All right. Cohesion is related to surface tension, which is a measure of how difficult it is to break the surface of a liquid. And so if you've ever been in a pool and you've seen an insect walking across the top of that pool of the water in the pool, that is due to the surface tension that's being created here. So we've got those hydrogen bonds holding these water molecules together, basically creating like a film on the top of that surface that's allowing for this insect to be able to walk across this water. So a checkpoint question that you can think about here with this new information is that after a hard workout, you may notice beads of sweat on your face. Can you explain what holds the sweat in droplet form on your face? Think about these properties of cohesion and adhesion. Here's an illustration of what I mentioned before with this insect walking across the surface of water. That is due to surface tension, which is a combination of both adhesion and cohesion. All right. Water transport. There's another property, capillary action, that allows for water to move through small, narrow tubing, for example, through veins and roots of a tree. All right. So again, due to sort of a combination of both adhesion and cohesion, capillary action allows for this water to traverse up these small tubes. Water's hydrogen bonds moderate temperature. All right. So heat is absorbed when hydrogen bonds break and are released when hydrogen bonds form. This helps keep temperatures relatively steady. Okay. As the most energetic water molecules evaporate, the surface of the substance cools. All right. And so there is a direct relationship between the presence of hydrogen bonds and temperature, okay? When a substance evaporates, the surface of the liquid that remains behind cools down. This is a process known as evaporative cooling. So, another checkpoint question to think about. Explain the popular adage that it's not the heat, it's the humidity. How does that relate to the presence or absence of these hydrogen bonds? Okay. Other properties of water. We know that water can exist in different states as a solid, liquid, or a gas. Ice, for example, floats because it is less dense than liquid water, right? So we're saying that water can exist as a gas, liquid, or a solid. Water is less dense as a solid than as a liquid because of the hydrogen bonding. And therefore, when water freezes, each molecule forms a stable hydrogen bond with its neighbor, okay? As these ice crystals form, the molecules are less densely packed than liquid water. Because the ice is less dense than water, it floats, okay? This is one of the very common concepts that we should understand here as we're looking at these various properties of water. Ice floats because it's less dense than liquid water, okay? So there's ice where we've got some stable hydrogen bonding taking place. Liquid water, these hydrogen bonds are constantly being broken and reformed, and so it's going to be less stable as a surface, okay? All right, so we're still looking at water's life-sustaining properties, all right? Water is what we refer to as the solvent of life or the universal solvent. What do we mean when we say that water is the universal solvent? It's because water is used to create many of the solutions, okay, that we need and use to sustain life, okay? A solution is a liquid consisting of a uniform mixture of two or more substances, okay? So this solution is created when we've got a mixture of two or more substances in a uniform manner. So we have a homogeneous mixture of two or more substances where we can no longer identify, okay, the two substances that were mixed individually, okay? And so water's versatility as a solvent results from the polarity of its molecules, all right? And so it can dissolve many different substances, all right? Polar or charged solutes dissolve when water molecules surround them, forming an aqueous solution, okay? So I want you to be able to distinguish the relationship amongst these terms solution, solvent, and solute, okay? The solute is the particle that is being dissolved. The solvent is the substance that is doing the dissolving. In this case, it is water as the solvent. And the solution is what's created when we mix two or more substances together in a homogeneous manner, okay? And then we end up what we call an aqueous solution, okay? So jot these terms down. And as we think about the life-sustaining properties of water, like why is water so critical to our lives? What does it do for us? What does it add for us? Okay. And so one thing that it does is that it allows the formation of these aqueous solutions. All right. It is the universal solvent. Okay. An aqueous solution by definition is going to be any solution that is created when water is in fact the solvent. Okay. So checkpoint question to think about. Why are blood and most other biological fluids classified as aqueous solutions? All right. Why is that? All right. We define the aqueous solution as one for which water is the solvent. So why do we consider blood and other biological fluids aqueous solutions? All right. when solutions are made, we can consider these solutions in terms of their acidic or basic conditions. Okay, so in liquid water, a small percentage of water molecules break apart into ions. Okay, we then can use the pH scale as a measure or a way to describe how acidic or basic a solution is. Okay, this pH scale is something that you've probably seen before. We use buffers to minimize the changes in the pH changes in a solution. Okay, so we have chemical reactions going on and we want to try to maintain the pH of that solution. We can use buffers to do that. All right, so let's take a look at this pH scale. All right, the pH scale ranges from 0 to 14. Okay, and again, it can tell us how acidic or how basic or alkaline a solution is. All right, remember we're saying that this solution is created with water as the solvent. Okay, so the lower end of the pH scale from 0 to about 5 or 6, we have the acidic solutions. Okay, so examples of acidic solutions are lemon juice, vinegar, rainwater, battery acid. These are all acids. Okay, these are all solutions that are going to typically have an acidic pH below 7. At 7, we have what we call a neutral solution. Okay, pure water, human blood. These are examples of neutral solutions. All right. At pH 8 or higher, we have what we call basic or alkaline solutions. Okay. Examples of basic solutions are household bleach, ammonia, milk, of magnesia. These are all examples of bases. Okay. So we use the pH scale to measure the acidity of a solution. Okay. So again, we have our increasingly acidic concentrations the closer we are to 0. Okay. At 7, we have a neutral pH where the number of hydrogen and hydroxide ions are going to be equal. Okay. Greater than 7, we have our basic solutions where we have higher hydroxide ions. You should definitely be able to use this pH scale and understand its measures. Okay. Different types of solutions and their acidic or basic salinity. You should be able to describe for us what is an acid solution, what's an acidic solution, an example of a neutral solution, water, lemon juice being the acidic solution, a basic solution being bleach. These are commonly encountered solutions for our day-to-day lives. Okay, let's stop here.